Hello and welcome to this video. In this video we are going to talk about the solutions to exercise 8.2 on the topic of collusion, and in this exercise we are going to talk about repeated interaction. This exercise of course immediately builds upon the previous exercise 8.1, where we were looking at collusion but in a one-shot situation. So we are now considering the same world, the same model, the same competition, with one crucial difference, and that is we are dropping the assumption of this game being a one-shot game, right? Instead, we are now considering what happens if we have multiple periods. So if you have not yet solved the previous exercise, or if there's any questions regarding the previous exercise, I would strongly recommend going back to it first, understanding the previous exercise first, and only then continue watching the solutions to this exercise. Alright, with that out of the way, let's dive right into it. As I already said, this exercise builds on the same setting as task 8.1, so we have the same assumptions. But now firms play a repeated game for periods t equals 0 to capital T. So there's some final period capital T. The demand function in this market remains the same. We will just additionally assume that it is constant over time. So in every single period, the demand function is the one we already know from the previous exercise. And same is true for the marginal costs. Just the same as we already knew it from the previous exercise, and the same for every single period. Alright, let's talk about collusion in this multi-period setting. There we go. Alright, so for the start, let's have a look at the short-term incentive to deviate. So we are asked to show that the short-term incentive to deviate from the collusion for a firm is this delta pi, the difference in profits, delta pi. And more precisely, we are asked to show that this incentive is the difference between profits under deviation, pi d, and profits under collusion, pi k. All right, so pi d, the d stands for deviation, pi k, we already defined in the previous exercise, k for collusion. All right, now, we are asked to show that the incentive to deviate in the short run is exactly equal to this difference. And then we're asked to show how the incentive deviation, deviation incentive changes as the number of firms in the market changes. Alright, let's start by showing what we're asked to show, namely showing the short run incentive to deviate. Alright, so the incentive to deviate is already defined in this task, right? So let's just spend maybe one or two sentences on this, why it makes sense to think of the incentive to deviate in this particular way. So pi k is the profits the firms make if they stick to the collusion, right? So that is, so to speak, in this model of collusion, the status quo. That is the profits the firm earn each period if they continue to collude. Now the profits under deviation, of course, is pi d. So if the firm chooses to not stick with the collusion but instead deviate and choose to individually maximize the profits, then the firm earns profits pi d. Now the incentive to deviate is precisely the difference between these two profits, right? So if a firm can earn additional profits by deviating from the collusion, then this additional profits, of course, is precisely the incentive to do so. Okay. Now, if we have conceptually understood this, this equation, why the difference, the incentive to deviate is exactly equal to this difference, well, then we can simply rely on the previous exercise where we have found expressions for pi d and pi k as functions of n, right? And that's exactly what we're doing here. We are simply plugging in the expressions we derived in the previous exercise for pi d and pi k, both as functions of n. And if we then continue to rearrange it, to simplify it, we can show that this difference is equal to exactly the expression we were given in the exercise. All right. So again, simply plugging in the expressions for profits we have derived in the previous exercise and rearranging them. Now, subsequently, we were asked to show how the deviation incentive changes as the number of firms changes in the market. So what we are interested in is, well, how does this delta pi change for a change in n? And particularly, what we're interested in is how does this change if the number of firms increases? Well, immediately looking at the expression for this incentive to deviate, it's not quite clear, right? Because trivially, obviously, we have n in the denominator as well as in the numerator. So we cannot really tell how a change in n would affect the overall difference in profits. What we can do, however, is we can analyze what happens if n increases. And we can do so by simply considering two situations. The first one being the difference in this profits or the incentive to deviate for any number of firms n. And then we compare it to the incentive to deviate for any number of firms n plus 1, right? So if the number of firms increase, and that is, of course, for any number of firms n, we are considering a situation where there is one additional firm in the market. Okay, so let's simply let's compare these two expressions. So we simply plug in n into this expression, and we are plugging n plus 1 into this expression, and compare these two situations to one another. This is, in the second step, you can see what this should look like if you plug in n and n plus 1 respectively into each of these sides of the equation, and then solving this expression for n, we can show that this expression up here is true. If this expression up here is true, then this expression down here is true, right? That's mathematically conceptually what's going on here, right? We wanted to show that the profits, the incentive to deviate is larger for n plus 1 than it is for n. And what we have shown here is that for any number of firm n larger than the square root of 0.5, this expression is true. Right? So we started with an expression, and now we found the condition, the interval of n for which this expression up here is true. Now this interval is quite interesting because, well, the square root of 0.5 is a number smaller than 1, right? So what we can see here is that for any number of firms, any feasible number of firms, this expression is true. So for any feasible number of firms, anything larger than square root of 0.5, it is true that the incentive to deviate increases if there is one additional firm in the market. Quite a curious result. So the more firms in the market, the bigger the incentive to deviate. All right, so why is this true? If there's two mechanisms behind this driving this result. So if there is more firms in the market, what the first part is that each individual firm has a decreased profit under collusion, and that's quite easy to see if you consider the profits under collusion of the individual firm, and we discussed this in the previous exercise, of course, where simply the overall profits divided by n, and then obviously for an increase in n, this number goes down. And the second mechanism then is the increase in profits in case of deviation, and for this we would have to look at pi d. Pi d, where do we have it? Right? Skipping all the way back to the previous exercise, you already should know the slide. Pi d was over here, and in this, if we were to calculate the derivative, we were able to see that, yeah, this increases, this incentive to deviate increases in the number of firms through this mechanism as well. All right, this is where we were. So, all right, so two mechanisms that drive this result, two mechanisms that are the reasons behind this increasing incentive to deviate for any increasing n. The first one being a decrease in the share of profits under collusion, and the second then the increase in profits in the case of deviation. All right. So now we have learned that there is a positive incentive to deviate in this model. So in the model where firms are in a chrono competition, right? Now we're asked the question if and how it would be possible for firms to stabilize the collusive behavior. Okay, we're asked to find the general terms. In general terms, what the long-run future loss is in a consequence of the deviation. So, and in the case of deviation, we are going forward from here and until the end of the semester, basically. In the case of deviation, we are assuming that all firms return to the optimal quantities of the one-shot in the one-period game. What this means is, as soon as one firm deviates in some period t, then of course in this period t the deviator is making the deviator's profits pi d, all other firms are making the non-deviator's profit pi f, but in any period subsequent to this period where the deviation happened, so in any period t plus 1 until eternity, we will assume that all firms go back to competition. So from period t plus 1 on, every firm will earn the profits which we called pi with an index IC for chrono competition in this case, or for competition in general. This strategy, of course, is nothing we came up with. Instead, this assumption is called a Grimm trigger strategy. So Grimm trigger strategy in the sentence would be, in case deviation happens, all firms revert to competition in subsequent periods. All right, we are going to assume for this exercise and for all the coming exercises that all firms are playing this, or yeah, that all firms are sticking to this Grimm trigger strategy. And now, of course, from this Grimm trigger strategy, there arises an interesting problem, and that is, well, we know that under collusion, profits of the individual firms are higher than under competition. Otherwise, they wouldn't do it. And that's obviously true in this model as well. So what we are now looking at is a situation where in the short run, deviation is profitable, as we saw in task A. But in the long run, firms are losing out on the collusion profits, right? Because in the long run now they are competing after the deviation. And in the following, we will have a look at this precise trade-off. Okay. And whether and how firms will be able to prevent the deviation using this trade-off. So let's start by stating the long-run future loss as a consequence of the deviation. So the long run loss is the change in the present value of future profits, right? We are now going to have to talk about present values of profits because we're now entering this multi-period world where, of course, if you want to compare cash flows over multiple periods, we will have to consider them relative to some base period. We will have to discount them basically into the present in order to compare them. So the long run future loss then is the change in this present value, in this discounted value of the cash flow of all future profits. Now, where does this change come from? We have already discussed it, of course. Well, if now in the future firms are no longer colluding, but instead they are competing, of course, we have a change in each individual period's profits, which of course implies a change in the discounted value and the present value of all of these future profits. If we want to discount these values, if we want to calculate the present value of these values, we of course have to assume that there is some discount rate, and we call it R, some discount rate R, which we can use to project streams of payment from one period into another. And what's quite easy to show is then that the discount factor for some discount rate R is equal to 1 over 1 plus R. And because that's a little messy to write down every time, we will call this discount factor gamma. No, delta. Discount factor delta. All right. Yeah, with this groundwork laid, we can then consider the present value of profits in case of collusion and in case of deviation, respectively. So let's consider first the present value, capital V, in a world where firms are sticking to collusion. And that, of course, means that in every period, starting from some period 1, going all the way to some period capital T, some final period capital T, each firm, if they stick to collusion, will make exactly the profits pi k under collusion. The only thing we now have to consider in addition is this discount factor, and as you're probably familiar with, we will have to apply this discount factor exactly once for each period we will have to discount. So if the payment is happening in one period from now, we have an exponent of 1. If the payment is happening in 2 periods from now, we of course will have to discount it twice, once for each period, and so on. So we will have this sequence of exponent all the way up to delta with an exponent of t. Now the sum of this geometric series of numbers can be shown to take this value, this sum. So 1 over 1 minus this value, which is delta over 1 minus delta multiplied with the profits under collusion. We will not need to derive this result. We can simply use and apply it in the context of this exercise class. But if you're interested in this, I would strongly recommend looking into the sum of finite or even infinite geometric sums. And I believe we are also talking about this in the lecture as well. All right, so point being, if there is a reoccurring payment in each period starting from today going until some period t, well then the present value of all of these cash flows is simply discount rate divided by 1 minus discount rate multiplied with the payment we are receiving in each and every of these periods. So pi k in this case. So with this, we have calculated the present value in the long run of sticking to collusion in the long run. The second point we were asked is the long-term profits in case firms are deviating. And we said that if they are deviating, then in the long run, they will revert to competition, grim trigger strategy. So the cash flow in each single period in the long run after the deviation will be the profits of firms under competition. So the calculation is exactly the same as it was under collusion. The only difference, of course, being that the profits are different, because now firms are making the profits under competition, no longer the profits under cooperation. And with that, then of course we can find out that this down here is the present value of long run profits after deviation. All right. All right, so we calculated we talked about the long run future loss, and we also talked about the present value under collusion and the present value under deviation. So now we have all the tools to finally calculate the change in profits in the long run, switching from collusion to competition, right? So very similar to what we did in the short run when we were comparing profits under collusion and deviation. We are doing the exact same now, but now considering the long run, of course. And in the long run, the change in profit is precisely the difference in these two series of cash flows, right? So it's precisely the difference between these two present values we have discussed on the previous slide. So the long run change in profits is the present value of the long run profits under collusion minus the present value of the profits, of the long run profits, if one firm deviated. All right, so now we have the difference, let's mark this one, the difference in the long run from the difference in profits in the long run if one firm deviates. And previously under task A, we have calculated the difference in the short run if one firm deviates. Or conceptually, one might think of this as what we did under task A, the short run change in profit from deviation as an incentive to deviate. Meanwhile, this change in the long run profits is conceptually a punishment because we are giving up on future profits. Okay? In this comparison, that will become important. Because if we now want to analyze whether firms can stabilize collusion, we are implicitly asking whether or not it is possible that this short-run incentive is outweighed by the long-run punishment, the long-run reduction in profits. So if we want to understand if the short-run incentive is larger, well, let's compare these two changes in profit, short run and long run. So we have a change in profits as we defined it under A, which of course means the change in short-run profits or the short-run incentive to deviate on the one hand side. And then we want to show or want to find the conditions under which this incentive is smaller than the long-run punishment of deviating and not sticking to collusion, because of course we are asking whether or not firms can stabilize collusion. So we want to find the conditions under which the incentive to deviate is smaller than the long run change in profits. All right, so we have calculated the short run incentive under task A, and we have calculated the long run change in present value, the change in present value of the long run profits as well. So let's now compare these two. And of course, collusion is stable only then, if and only if, so to speak, if and only if the incentive to deviate is smaller. So if this statement is true. Let's consider next under which conditions this statement might actually be. We are doing this in task C, where we are asked to determine for n firms the present value of profits in the competitive case, in the collusive case, and in the case of deviation. And then we are asked to calculate, and that's a very important concept throughout this course, we are asked to calculate the critical discount factor delta crit as a function of the number of firms. All right, so we have already discussed present values, and if we want to define the present values of all of these scenarios, we can reapply what we already know. Let's start with the present value of sticking to competition. So VC, the present value of competition. Now, if firms choose to compete, well then in each and every single period they make profits pi c. There is no difference in profits happening, they just stick to this strategy. In each and every period they gain these profits. And then what we can show is for a starting index of I equals 0, so we are now starting in period 0, we are not considering the profits, the long run profits starting from next period, which we did previously, but instead we are now considering the short and long run, the overall profits, all profits in total that result from this strategy, so the present value of all of these profits. And what we can show that for this type of geometric series, where the first power is a 0 and not a 1, we can show that this geometric series collapses to this very simple expression. So the present value of sticking to competition, present value VC equals pi c divided by 1 minus delta. All right, that is the present value under competition. Let's now consider the present value under collusion. Under collusion, the idea is exactly the same, right? Because by assumption, if we are calculating the present value under collusion, we are now considering a world in which firms stick to the collusion in each and every single period from here until eternity, or from period 0 to some final period, capital T. So mathematically, this is exactly the same. There's only one minor difference, or one crucial difference, however, and that is, of course, the profits in each individual periods now are pi k, so the profits under collusion. Okay? And of course, we know that the profits under collusion in this type of model, in this world we are discussing throughout this assignment, the profits under collusion are larger than the profits under competition. I mean, logically, otherwise why would they collude, right? And if the profits firms earn in each and every period, pi k, under collusion, are larger than the profits they would otherwise under competition, pi c, well then logically the present value of these profits under collusion is larger than the present value of the profits under competition. And that is what is written down over here. So we immediately know that for any given pi c smaller than pi k, that the present value pi c must be smaller than the present value vk as well. All right. Now to the third and final present value we will need to discuss, Vd, so the present value of deviation. This one is slightly different and therefore a little more interesting, because what we need to consider is Grimm trigger strategy, right? By assumption, in this world where one firm deviates, the deviator deviates in the first period. So in this first initial period, deviation is happening and the firm makes profits of the deviating profits, so pi d. We calculated it previously, if you remember. So in this first period, in the initial period, this firm makes profits pi d, profits under deviation. And then, by the logic the Grimm trigger strategy, in each and every subsequent period, the firm is making the profits under competition. So what we will have here, if we sum this up, is, well, we have pi d plus this geometric series, which is a function of the discount factor in pi c, starting with an exponent of 1, because it's starting in period I equal 1. So exactly the same expression we had on a previous slide, right? So we can calculate this and we can find out that the present value of deviation is pi d, no reason to discount because it's happening in period 0, plus the present value of competition profits starting from period 1. All right, that is the present value of profits under competition, under collusion, and under deviation. Now finally we are asked to determine the critical discount factor delta crit. The critical discount factor is defined as follows. The critical discount factor is that discount factor under which collusion is stable. All right, so we can start, or we find the critical discount factor from this starting point. We want to know under what conditions, or condition in this case, collusion is more profitable than deviation. All right? And the answer to this inequality, the answer to this question, then provides us with the critical discount factor. Now, if we plug in Vk, which we have stated above, and Vd, which we have stated above, and rearrange these expressions, we can find out that this is the case. So collusion is stable if this inequality holds. So if delta is bigger than, and then this fraction of profits where we have pi profits under deviation minus profits under collusion divided by profits under deviation minus profits under competition. And now, as I said, this delta, this discount factor for which this inequality just barely is holds, under which collusion is stable, is defined as the critical discount factor. And of course, if we now use the profits we have calculated earlier, right? Remember, we are still in a setting where we actually have a whole full-blown model in somewhere on the previous slide in this exercise, right? We have demand functions, we have n for the number of firms, we have cost functions, etc. So we actually calculated pi c, pi k, and pi d in previous tasks. We can now take these results, plug them into this expression we have just derived for the critical discount factor, and if we do so, we then have a function delta crit that depends on the number of firms in the market. So this is the critical discount factor for the very model we were discussing throughout this whole exercise 8.1 and 8.2. All right, so in this market, this is the critical discount factor as a function of the number of firms in the market. All right, now let's get rid of n, so we have some actual results that we can talk about in a more straightforward way. So in this task D, we are asked to consider a case where n, the number of firms, takes a value of 3. And we are asked to determine the critical discount factor, delta crit, which determines whether the collusion is stable or not. Well, we have already stated an expression for this critical discount factor, so we could simply plug in n equal 3 and calculate it. All right, and then we're done. What we can do, just to reiterate this whole concept of the critical discount factor, and just to go through this thought process one last time is we can again compare the short-term incentive to deviate with the long-term punishment of deviation, or the short-term change in profits with the long-term change in profits. And only if the short-term change in profits is smaller than the long-term change in profits, well, only then collusion is stable. And only for a delta for which this inequality is true, collusion is stable. All right, so we have found expressions for the short run change in profits through deviation, right? Just as a reminder, delta pi was the difference between delta d minus delta k. The difference in profits, delta pi, was equal to the difference in profits under deviation, pi d, minus the profits under collusion, pi k. If we plug in the numbers, and we even calculated the incentive to deviate in one of the previous tasks, of course. If we now plug in the number of firms n equal 3 that was given in this task, we find out that this short-run incentive to deviate takes a value of 277.778. Now, our point of comparison, of course, is the long-run loss in deviation. So we want to calculate the present value of this reoccurring difference, loss in profits that we have by the logic of the Grimm trigger strategy. All right? We have, of course, stated pi k and pi c in previous exercises, so we can simply plug in the expressions for this. And if we do so, we can find out that the long-run loss through deviation is this expression, delta divided by 1 minus delta times 208.333. And we immediately see that logically the valuation of this long-run loss in profits, the valuation of this decreased future profits depends on the discount factor delta. So, now we have all the ingredients we need in order to make this comparison, where the short-run change in profits, or the incentive to deviate, so to speak, needs to be smaller than the long-run, foregone profits that come from the logic of the Grimm trigger strategy. So we simply plug in delta pi, 277 and we plug in delta pi in the long run, which was calculated at this expression over here, and then we can solve this expression for delta. And if we do this, we can find out that delta is rounded to 3-digit 0.571. So the critical discount factor in this model, in this Kono model, for the given demand function, for the given cost function, for the given number of firms, of course, for this setting, the critical discount factor takes the value of 0.571. Okay, now let's talk about what probably already is in your minds. That is, we have assumed that this market exists for periods 0, 1, 2, 3 until some capital T, which implies that there is a final period, capital T. Now that's a problem, and why that is a problem becomes maybe more obvious once we go through the solution to task E. So we assume that all companies know that this market will exist for exactly 5 more periods. Or what this means is, of course, assume capital T equals 5. After that, demand collapses. There's some reasoning behind this. Does not even matter what exactly it is. It's just there is no market afterwards. There is a final period of, after which this market ceases to exist. Now, in this scenario, where firms can already anticipate that there will be a final period for this market, in this scenario, is it even possible to stabilize collusion? because this whole logic we applied earlier, of course, only worked because we were taking the sums of infinite geometric sums. What happens if these sums are no longer infinite, but rather have some final period, for example t equals 5? Now, it is probably the easiest to answer this intuitively, and that means we can simply, because now we converted this into a sequential game with finite periods, right? And we already know the tools, or a very strong tool to analyze sequential games. So let's use the tools we already have in our hands, and that is backwards induction. So let's start with this final period, capital T, or 5 in this case. Now in this final period, of course, all firms are considering, well, do we want to stick with the cooperation, with the collusion, or do we want to deviate? And as we have seen earlier, in this scenario where there is no tomorrow, so we really are back into the one-shot world, in this scenario is always a best response to deviate and to compete, or in other words, to choose the individually profit maximizing quantity. All right, so in period 5, we know deviation is profitable, we know collusion cannot be stabilized, right? Because there is this whole effect of loss in future profits does not kick in. There is no future profits anyway. All right, now we know in period 5, in this final period, deviation is profitable, collusion cannot be stabilized. Let's move one stage up in this sequential game and consider the previous period, period 4. Well, now, of course, we know that in period 5, deviation is profitable. What does this mean for period 4? Well, of course, in period 4 now, there is no punishment from deviating because we are behaving competitively anyways in the subsequent stage, right? So, of course, it is profit maximizing, it is long-run profit maximizing to behave according to the individual profit maximization already. It's not profitable to stick to the collusion because we already know that in the coming period we are no longer playing collusion. All right, so this result simply continues to move up this ladder in this finite game. So because in period 5 deviation is profitable, well, that implies that in period 4 or t-1 deviation is profitable, and we can assume this all the way going back to period 1 or to period 0, so up until today, which implies that as long as these firms know that there is some final stage, some final period where the market ceases to exist afterwards, as long as firms know that, there is no way to implement collusion and to stabilize collusion. This result is called the Selten theorem, which generally reads that in a finite game with a single Nash equilibrium, in this case deviation or competing, this equilibrium is realized in all periods and not only in the final period.